Hello, hope you're doing well. Next talk is provided by uh, cypherpunk, crypto-anarchist, computer scientist Frank Braun.
Thank you very much. Does it work? Can you hear me? Yeah? Okay. Okay, I'm going to talk about In Code We Trust, fighting targeted backdoors with secure multi-party code reviews and a single source of truth. Quite a mouthful. Yeah, he already said it. I'm a crypto anarchist software developer, and I became somewhat, disillusionized with mainstream technology. Last year, I gave a talk about dehumanizing technology, which where I see that we are actually on a trajectory in technology, in my opinion, that would lead to technological totalitarianism. And for me, that was, quite depressing. And because I didn't really have a solution, I still don't really have a solution. I actually tried to submit the talk somewhere else afterwards, and they rejected it because they said, yeah, it's interesting, but what's the solution? And so I thought about that problem, and for me, it always comes down to three things. We can do political reforms. If you're into that kind of thing, good luck. For me, usually, it seems to me a waste of time, at least for my resources. And the other thing I could find in the literature is like this, the abolish method. So, we bomb ourselves back into the Stone Age, which is what Kaczynski is suggesting in the anti-tech revolution, Why and How. Well, it has some merits, but it's a bit, immoral to kill off a few billion people. So I'm not into it that much as well. So for me, the only solution, is, especially, coming from technology, is we need to kind of transform technology, and it means we have to grow on a trajectory of technology which leads to a better world faster than the suppressing technologies grow. And so that's what I'm going to talk about today. So that's, general what I'm interested in is freedom technologies. How can we engineer technologies that make us freer? And we heard a great talk yesterday from Smuggler about that and what crypto anarchy is and what we need to build there. And but this isn't really about, crypto anarchy. It also means sometimes we have to, build some base layers, which we need to deliver our crypto anarchistic software to the world. And so this is about, trust. There's a famous Turing Award lecture from Ken Thompson, is the inventor of Unix, and he wrote, to what extent should one trust a statement that a program is free of Trojan horses? Perhaps it is more important to trust the people who wrote the software. And that poses the question, how can we trust the people who wrote the software? And also, more importantly, for this talk, how can we make sure that we actually run the code that these people wrote? So this talk is not about making sure the code you execute is right. That's a hard problem in and of itself, but it's about to make sure you execute the right code. So because what happens if you execute the wrong code? You're owned. And I mean, we can build the best, cryptocurrencies and encrypted messengers. If you have backdoors in that technology, then it doesn't help you at all. And last year, Smaga talked about that in the fog of crypto war, that this whole debate about crypto regulation is often very falsely painted, because a lot of pro-crypto people, they think that the debate is about crypto regulation. They think it's black and white, and that the statists are so stupid that they want to outlaw cryptography totally, and that's never going to work because you cannot outlaw math. But that actually is wrong, and he then, describes realistic approaches to regulate cryptography in general. So one thing is that they definitely want to keep the metadata, even if you encrypt all communications. Metadata is very helpful in surveying people. They want to nudge vendors into delivering software with less secure defaults. They want lawful hacking. You might have heard about state Trojans. And what I focus on today is the use of update mechanisms to deliver police Trojans. So if you can subvert an update mechanism for a software program or an operating system, you can actually target backdoors to people, and thereby you can surveil certain people without, building backdoors into every piece of software. Or you could also just mandate plain text access, but that's not so likely. And so that was kind of determined as the most probable method that regulators would take to regulate cryptography. And in this presentation, we're going to focus on technical mitigations, because I said already, I'm more into the technical mitigations, not the political ones, to this issue of targeted updates. Because with a targeted update, you can introduce a backdoor into a specific device, and then you can have so-called targeted backdoors. So, the suggestions from that article were that we need a secure software distribution. So we have to make sure that every user of the software actually sees the exact same version of the software. And we have to make sure that the software development itself is actually secure. That means we need to better review and audit security critical code. And ideally, we want to enforce that always 2 developers or more, you can configure that, sign off on changes. Otherwise, developers could introduce general backdoors into the code. We'd also like, verifiable build processes. A lot of work has been done in that area with reproducible builds. And ideally also, we want more decentralized platform vendors. Today, most users, they depend on a very small set of platform vendors. You have Apple, Google, and their app stores. And so as legislators, you only have to focus on a few vendors in a few countries. And when you can regulate them and force them to push targeted updates, you basically control the whole ecosystem. And that ideally, we would also like to change, but not in the first step, because first we have to build the technology and hopefully bring it into open source projects. And then we can put more pressure on vendors. And also, we're not going to focus on that, verifiable build processes, because if we actually solve the first 2, everybody sees the same source code, and we make sure it's signed off properly, then the user can build the source code for himself. I'm most interested in that, because if you're dealing with security critical code, you kind of have to give the user the source code anyway. It's not very useful when you just push them, let's say, a binary wallet, a binary program for cryptocurrency wallet. So I'm going to explain how we implemented that, but first, just give you some background on recent developments. So last year was the prediction. That's what's going to happen, targeted updates. So unfortunately, that's exactly the approach the Australian government, which is a member of the Five Eyes, is taking in the proposed Assistance and Access Bill. It says, technical capability notices may still require a provider to enable access to a particular service, particular device, or particular item of software, which would not systematically weaken these products across the market, which is kind of lawyer speak, but it means how do you make weaken every device? You just push to certain people, and in all these app stores, you already have a binding between people and their software. Let's say the Apple Store, you log in with your Apple ID, and then of course they know who you are. And I think it would be a mistake to think, it's the crazy Australians, and it's not affecting us. But this is like, they're just spearheading it for the Five Eyes, and that would mean it will come on other Western countries. And as we, in the, China and the others, they're probably even worse already. So it also has this part in it where it says, likewise, a notice may require a provider to facilitate access to information prior to or after an encryption method is employed, as this does not weaken the encryption itself. And that, of course, means if you translate it, it's the same mechanism. Just you push a targeted update, which introduces a targeted backdoor, not into an app, but into the whole operating system. So, next time you update your phone, it says there's a security update, and then boom, it was an insecurity update. And so just to give you a review of what is actually deployed. You know, most systems who try to prevent these sort of attacks, they're actually quite simple. You know, they kind of have some public key which is known, and they sign off on packages. And then you have your trusted public key in your system, and then you install something, it's verified. For example, in Debian and Ubuntu and all the other derived distributions, that's exactly the model. You know, you have this key ring, which has like trusted keys, and then it installs apps. And which means, of course, the reverse conclusion, everything is trusted as soon as it is signed by this key. And was very interesting for me, I always thought, you know, that the developers have anything to say in the process, but it's actually not true, you know. This depackaged thing has the ability to verify GPG signatures from the actual package files, but that's not what actually happens. What happens is you only verify the repository metadata. So the Ubuntu or Debian repositories, they sign off packages, and that's what you verify. You don't verify anything from the developers. You hope that the Debian guys would actually, verify that. And these keys, you can just look it up. I think it's like up key list or something. You just see all the keys that are trusted on a Linux distribution. They are like 6 years old often, because it's very hard to rotate GPG keys. There is no method for that. So I think this has had like multiple problems. Like I said, the developer signatures, they do not matter at all. The repo signatures are created by a single GPG key, which is often like quite old and kept on a network server. If you look at the documentation, basically the way to set up Debian repositories is you put a network server with a hot GPG key, and every package you push, it automatically signs it. So unless, I hope they have a more secure setup, but I'm not sure. And that also means, so it's easier to steal these keys, and it also means that the signing is automatic. So it's not that likely that everybody, that the source code is actually checked. And like I said, there is no method to rotate keys easily. So what they usually do is they introduce a new key, and then for a period they sign with 2 keys, and at some point they phase out the old one. So if a key leaks, there's no default method to revoke it. And the last one, I'm not sure. If somebody knows more, please let me know. But it seems to me that there is no pinning between keys and repositories. At least in GPG, that's not the way it works. GPG looks like it's a public key in your key ring. So that would mean that as soon as one key is leaked, you could sign off packages from all repositories. So that's like one big solution for the operating system level. And what could be is like a generic way on the source code level. So as probably many of you know, Git is like the most widely deployed version control system. And there are 2 things you can do in Git to secure code. You can either sign tags or you can sign commits with GPG. So sounds good, but the problem is tags. You can just sign a tag. Tag points to a certain version of the source code, but they're not fixed. You can always, change the tag later and sign it again. So you're not actually sure that a signed tag points to a defined version of the software. So they're not unmodifiable. The other thing you could do is you sign commits. But if you actually want to do it, that means if you want to verify these signatures when you pull in source code, that means you have to need a signature on every single commit, and then pull it in with verify signatures, and only merge these so-called fast-forwarding branches. And it also means that you have to trust all the signatures, like from all developers, or they would need a process where they only sign with 1 key and change every commit. So it's not really widely used in practice. I mean, people sign releases, but it's not like they sign off every commit. And you still need to know the head. And I already said that. So it's hard to deploy in practice. And so these methods, the most widely used at this point, they do not protect against key compromise. Once the key is compromised, you can push targeted updates. You cannot protect against developer coercion because it's always one key. So you just need to go to one person or one organization and then force them or blackmail them or bribe them to give up the key, and then you have access. And you also have the regression problem. You know, when you, let's say there is a critical bug is found, then it's not easy to, you can prevent the update. Often that's enough to do, you know. Problem was found, but if you prevent people from updating and fixing the bug, you can exploit that bug. So yeah, developer being forced to give his key would be disastrous. And as I already said, you know, we cannot easily rotate out of these keys. And so the proposed solution for this problem is to improve on these two areas, you know, secure software distribution and development. First, we need to establish code trust, and in a way where multiple parties, they review recorded changes in a hash chain. So you always have an unmodifiable history of code changes and sign it off by more than one person. And that prevents that you can, you know, introduce a generic vulnerability. And the second thing you need is you need a single source of truth mechanism which makes sure that every user gets the same software. So basically you have this, you know, unmodifiable hash chain which records everything, but you always have to make sure that everybody sees the most current version of this hash chain. And when you actually, if you combine these two, you have a system where you can build secure software, deliver an update, and which cannot be compromised by a single developer, and which makes sure that everybody gets the same software. And so that's what we designed together. Smuggler designed most of the stuff, and then I wrote most of it. And so just to, you know, so now we're going more technical. How the system actually works. So we're dealing with units of code. It's similar to Git, but it's an orthogonal system. So the idea is you kind of use Git or whatever version control system you use to develop your source code, and then you kind of have this releases you sign off. And we didn't want to pull in like Git as a dependency and have, you know, I mean, this is a very safety critical piece of code, so we want to keep it as minimal as possible and just make it do the job that it is built for, and it's not version control. So the thing we're dealing here with is units of codes are directory trees. You know, you have a directory tree with files in them, and you can hash entire trees, and you can create a tree hash of all the files. It's similar to a normal hash. And so what a code history is, it's basically a sequence of unique tree hashes starting from the hash of the empty tree. And in contrast to version control, there are no branches. So it's always, you know, changes, one change after the other. And then you record signatures over these trees in a hash chain file, And these signatures, they contribute to a threshold. So it's like similar to multi-signature Bitcoin transactions here. So you could say, so the system itself, for example, it has a 2 out of 3 scheme. 3 developers, 2 have to sign every release before it gets published. And then you just distribute the code as a set of patch files, which you then, you know, you take an empty directory tree and you just apply all the patch files one after the other, and that way you can recreate the code. And you just name them after the outgoing tree hash A, which, if you think about it, implies that you never can go back to the exact same version, which is kind of what you want. Okay, so yeah, just so to explain you in a bit more detail all the components. So tree hashes, yeah, you just, you know, you hash all the files, you record the permissions, and then you have a new text files containing all the files in a directory hierarchy, and you hash that. And it's basically exactly the same if you would just pipe it through SHA-256. Then you have patch files, which is also, you know, properly specified, and it's not for, you know, human readability. It's optimized to just, you know, make sure that it's a robust format. And then the most important component is the hash chain itself, and it's just, you know, a new line separated file where each hash chain entry corresponds to a single line of the following form. You always have, you know, space-separated fields, and the first entry is just the hash of the previous line. Then you have the time when you created that entry. Then you have a type, and then you have type fields for the type. The fields are separated by white spaces. Current time is in ISO hashes, SHA-256, and hex encodings have to be lowercase, so it's a unique format. And we just use ED25519 keys and encode them in base 64, and just allow arbitrary comments. And just to walk you shortly through the different types. So you have a start type, source, signature, add key, remove key, a signature control. And you always start with the C start type. And basically, you hash the empty tree. No, this is a hash of the previous. You hash the empty tree. And you start with the empty tree of code, and you introduce one public key, which is the person who started the project. And then you can add code where you basically add the source hash of the entire tree and sign it off. And sign off that you added the code, and then there's a different type which basically signs off on previous lines. So that would be the review process. So you always have the publication process where one developer says, here's the new version, and then you have the review process where developers add signatures to sign off on that change. And it doesn't necessarily have to be on the refer to the previous line, so you can have detached signatures. So usually you would have one developer creating the hash change file, and then others doing reviews and just sending him their signatures. And the other types basically deal with managing the set of signers. So there's add key, which adds a new signer. There's remove key, which removes one. And there's signature control, which basically sets the number of necessary signers. And so if you would create a, let's say, 2 out of 3 signing thing, you start off with an empty hash, and then first you add the other keys, sign off on that, and then you start adding the code. And that also means that you always can do key rotations or adding developers, removing developers in a secure way, because it's always secured in that hash chain. And if you combine all of that, you have solved the first problem. You make sure that you need multiple people to sign off the code. It's a defined version of the code, but it doesn't solve the regression problem, because you still have to make sure that everybody gets the current version. And that's where you need a single source of truth. And in order to distribute the head to everybody. And so then they can verify everything. And so what we do there is we just use DNS. And DNS is a very widely used single source of truth system. And what you do is you take the head and you sign it and you put it in DNS as a TXT record. And then everybody can verify it. And because DNS is a distributed caching system, you're not actually talking to the person who does the publishing. So he doesn't really know who's querying the TXT records. So that means he cannot send you a targeted head. And it also means that once you see a signed head for the first time, you cache the public key, and then new heads must be signed by the previous public key. So it's the trust on first use system. And then the big problem you have is, which remains, is DNS spoofing, where in DNS spoofing you basically can introduce wrong signatures, wrong data into DNS. And there are 2 cases. Case number 1 is you've already seen the public key before, and then you cached it. So DNS spoofing cannot attack against that. But you have never seen an entry before, then you could be spoofed into accepting a totally wrong software. And the way to mitigate that is that you just use a domain with DNSSEC enabled, and DNSSEC basically signs off all the entries in DNS itself, so you know it's from the person who actually publishes the domain. And that way you have a secure way to distribute the head of your code chain. And yeah, and the way it basically works is, you know, we have all these different fields, a pub key we rotate to. Then we have the validity of the head, from when to when it is valid. We have a counter, so with the counter you make sure that the signatures are always increasing. You have the actual head, which you want to publish, and then you have a signature over all the other entries. And you just concatenate that into a byte array, encode it, and put it into a TXT record. And so now we have the components, we have the code chain with the patch files, and we have the TXT record with all the with the head, which is signed. So how do we bundle that together and distribute software? The way we do it is we have a secure package. Secure package basically specifies a piece of software. It needs 4 pieces, you know, the actual name of the software, the current head, then the DNS, where you can query for the most current head, and then the URL where you can download the patch files. And so, for example, for CodeChain itself, it has the current head here. Then this is a DNS domain you use for querying the TXT records, and under that URL we have the patch files. And so you just need a few operations now. You need to create a package initially and then sign off changes for updates. That's basically what an administrator does, and every time he does it, he has to update the TXT records. That's currently a manual thing, but should be automated in the future. And then on the user side, he needs to get a secure package file from somewhere and install it, and then later query for updates. So here you can see an example where we query the TXT record, and then here it has the signed head. And so basically all you need from somewhere, somebody just give you this secure package file, and you know, make install, and it verifies everything, and you are sure that you have exactly the same software as everybody else. And yeah, that's shown here. You know, you have this package file. It asks for the signed head, downloads the distribution, which contains all the patch files, and then and the hash chain verifies the hash chain, the signatures, the patch files, and then just compiles it and installs it. In this case, we use Go because all the code is written in Go, but the installation procedure is in a way that it just, you know, calls a makefile. So the idea is that you have source distributions which are self-contained, and the user has the necessary compiler, and that's it. And so in the program, we actually have 3 tools and 3 roles. So CodeChain itself is to deal with the hash chain I described earlier, which is for the developers. Then you have the single source of truth pub for the administrators, who are then publishing the signed head, which could be done automatically. You know, I mean, it's not like I said earlier for up, because the integrity of the code is just determined by the developers. This is just for publishing the head. So what you would actually want is you have a cron job who always signs the head every, let's say, week, even if you didn't change anything, because the heads will expire. And that way you can also make sure that you always get the most current version. And then for the end user, it's basically just a SAC package to install and update software. And just some more information on the software itself. It's available in beta on GitHub. It's a minimal code base, Go only, cross-platform, tested on Linux, and it's around like 7,000 lines of code and vendor dependencies. So it's a self-contained package, public domain, and it doesn't depend on anything in terms of binaries. We just use git diff for the review process, but you can also do the review process in a way that you use different tools for that. And yeah, and it's, of course, we review and sign CodeChain with CodeChain, and 2 out of 3 signatures. And just for reference, this is the current head. And yeah, to conclude, while is it good that code signing is widely deployed now, it doesn't solve the important attack vectors, key compromise, developer coercion, and mitigation, regression. And that's what we all mitigate with code chain. And it basically then gives us globally identical, verifiable, reproducible, and attributable binaries built from source, which mitigates targeted updates. One more thing about that is faction or something like that. And it's the same here. I think you can build a much more elaborate system or solve more problems, but what we wanted to do with it is solve the problem we have, which is then later distribute secure software. You know, it's not about replacing the update process in the Apple App Store. I mean, it would be great if somebody does it, but we first, we have to solve our problem in a secure way, and hopefully others can pick it up, and thereby we move the entire ecosystem. It's a bit like the open BSD approach. You just fix your own stuff and make it really good for your own problem, and then hopefully others, will improve it. Because otherwise, I will spend the next 5 years doing that, and it takes a bit more, to get out of this trajectory we are than source code updates. Acknowledgements, I already said, Smugger did most of the design work, architecture, and here's my contacts, and you can also download the slides. I went a little bit overboard and wrote it all up in an essay of 25 pages. So if you're really interested in that, you can read the whole thing, and it has all the specifications of all the different functions in there. And thank you very much for your attention, and I'm happy to take some questions.
Thank you very much for the interesting speech. We have time for some questions. Yeah, I see.
Hi, thanks for the presentation. Would you be able to use a blockchain instead of DNS?
I was waiting for that question, thank you. It's the obvious one. Yes, you would be able to do it, but then you have the question: how do you talk to the blockchain? And if you have a device which is not very powerful, you don't really want to sync the whole blockchain on your device all the time. But it is definitely possible, and I would love to see somebody have an alternative head distribution mechanism, and blockchain would be the obvious one. Yeah.
Okay, let's see another one.
Yeah, I have a question regarding the DNS, whether it's dependency that's really needed. Can't you just use the URL that is in the package file to download whatever you need to verify?
If you just use the URL, if you resolve the URL, you're talking to DNS first, and then you talk to the server. But the problem there is that then you talk to the publisher, and the publisher can identify you. And with DNS, it's distributed, so that solves, it's very important to prevent the targeted updates, is that the publisher cannot see who's talking to him. It would be the same for blockchain. In a blockchain, the one making the entry cannot see who reads the blockchain. So it's really important to separate that.
Okay, another questions? Maybe I have one, which every developer likes. You said it's in beta. When we can expect the work will be done to prepare to release like full version?
Excuse me, what?
You said that it's in beta version right now.
Yes, yeah.
Then
Basically everything I talked about and showed you is already released and usable. What's missing is the automatic publishing of the DNS entries and the key rotation for the DNS entries. But everything else, we used it and it's working. Probably need even more documentation, but
thank you.
So I would be interested in knowing what are your ideas about preventing developer coercion? Should I maybe be talking about anonymous development?
Well, you kind of need to build reputation. So when you have no names attached, it's hard to build reputation. But the way you are prevented in that case is that first of all, you have more than one developer. And it depends how paranoid you want to go. You could have, let's say, 5 developers or 10, and at least 5 of them have to sign, and they're on different continents. So you would have to coerce like 5 developers at the same time. So it's the same thing with this multi-signatures for Bitcoin transactions. I mean, there's always this trade-off between how usable is it and how much coercion do you need to break the system. And I think this is a big step when the big step here, I think, is if you go from 1 to 2, you need. Because then, if one is compromised, let's say the others, they hear about it, they immediately revoke his key and rotate him out of the signing pool. And yeah.
Okay.
I would like to add something to the anonymous developer option. Sadly, we have stuff like cold stylometry. So if you have published code, you won't be anonymous anymore as a developer.
Okay. Yeah.
I just want to ask, is there a way of using the source of truth, something connected to IPFS and not DNS?
You said IPFS instead?
Yeah.
Yeah.
IPFS instead of DNS.
Yeah. I mean, there are many ways. I mean, you could distribute the head on Twitter if you like, or on IPFS. It's just one method.
Okay.
Yeah.
So no questions. So thank you, Frank.
Thank you.
Nice speech. I just want to remind you that at